This is the world's largest wind tunnel here at NASA's Ames Research Center in Northern California. It's used to test the aerodynamics of new aircraft to simulate the actual conditions of flight. But when it comes to experimental planes like the new National Aerospace plane, which can travel at speeds up to Mach 25, this wind tunnel becomes useless. Those kinds of simulations can only be run on a computer, on a supercomputer. Today we take a look at the incredible speed and power of supercomputers on this edition of the Computer Chronicles.
The Computer Chronicles is made possible by Leading Edge, makers of IBM-compatible computer systems, including word processing with spelling correction, communication software, and Hayes-compatible 1200 and 2400 baud modems. Leading Edge, with over 1,000 service centers nationwide. Leading Edge, leading the way to the information age. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover developments in computer technology worldwide.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, this is obviously not a computer. It's a model of the National Aerospace plane, the one I was just talking about. It's been nicknamed the Orient Express. It's designed to go at speeds greater than 15,000 miles an hour. That means
Incredible.
San Francisco to New York in 12 minutes. Now, you're a pilot in addition to being a computer expert, so I want to ask you, when these aeronautical engineers talk about aerodynamic simulation, what are they trying to find out, and why do they need a supercomputer to do it?
Well, first of all, Stuart, I've never flown anything that even resembles something like this, and also I'm not an aeronautical engineer. But I understand what they have to do is they have to compute the pressure and stresses on the entire surface of the aircraft through its entire flight envelope, going from a takeoff to effectively its outer space and back to a landing again. So that what they do is they use a big supercomputer that's equivalent to, say, 50,000 PCs, and you go along and compute at every point in the aircraft the pressure and stress, and then you do that for the entire flight envelope and analyze the results, make the changes. But the thing that really concerns me, though, if it only takes 12 minutes to go across country, then what am I going to do with my laptop?
Well, we're not going to talk about laptops. We're going to talk about the latest in supercomputers today. In fact, we'll see the world's newest and most powerful supercomputer system, the one at NASA's Ames Research Center. We begin with a visit to the Numerical Aerodynamic Simulation Facility in Mountain View, California, where the heart of the system is a new Cray 2.
Order! Freeze it!
On March 9, 1987, NASA's Ames Research Center in Mountain View, California, inaugurated a new supercomputer-assisted aircraft design center. The colorful ceremony signaled NASA's determination to be at the forefront of computational fluid dynamics.
17 years ago, the Ames Research Center initiated an aggressive effort in computational fluid dynamics. That is, the solution of the mathematical equations that govern the flow of liquids and gases. The visionaries who conceived this program knew that aircraft design was a trial and error process, and one that required thousands of wind tunnel test hours. They believed that computational simulation techniques could be devised, and that these techniques could accelerate the aircraft design process.
Up until now, computers in aeronautical design have allowed us to do things better. They have led to improved designs and greater efficiency in the design process. But with the vehicles that are now on the drawing board, like the aerospace plane, for example, NASA's enabling. It's not a matter of doing things better, it's a matter of doing them at all.
At the heart of NAS, or the Numerical Aerodynamic Simulator, is the Cray 2, a 4-processor machine routinely performing 250 million floating point operations per second, with a burst speed of over 1.7 billion calculations per second. The main memory holds 256 million 64-bit words. It has the processing power of about 50,000 PCs. To keep the compact machine cool, circuits are immersed in liquid fluorinert. NASA expects even greater speeds when a second supercomputer is added in late 1987, bringing it closer to its long-term goal of 10 billion operations per second. The massive power of the NAS hardware is aimed at solving the complex equations of simulated fluid flows.
the fundamental problem we're attacking is to be able to simulate the flow over an entire aircraft configuration. That's the fuselage, the wings, the tails, and to do this in a manner that captures the essential physics of the flow field, which is quite complex, and generally it's a turbulent flow field, so the flow is very chaotic and very complex. In addition, we've been able to do new flow fields that have never been done before in the areas internal to an engine, for example, flows inside the shuttle main engine.
Aerodynamic simulation has become the preferred way to design aircraft that would otherwise require extensive wind tunnel testing. The supercomputer can graphically recreate the physical forces on a particular wing or fuselage design through a process called particle tracing. The engineer selects points along the design from which to release particles. By tracing the flow of these particles, he can discover areas of turbulence or stress. The next step is to make the changes needed to improve the aircraft's aerodynamic performance. Without the simulated flight test, the only way to discover flaws is to create a string of models and test them over and over in a wind tunnel.
You still have to conceptually decide on your model, you still have to make a design, but the design always stays in a mathematical form, and it's easily changeable. So you put your model in the computer, get your results out, look at them, and change your model. It's what we call cutting and filing in a wind tunnel, cutting and filing in a computer rather than cutting filing in a wind tunnel.
The time-saving advantages of aerodynamic simulation are dramatic. The structural analysis of Boeing's newest aircraft, the 7J7, took only 10 hours of supercomputer time, compared to 12 days of computer time for the 747 and 21 months for the first B-47 jet aircraft, when a slide rule was the only computer. But supercomputer simulations provide more than just speed. The NAS system's uniqueness lies in its ability to simulate experiments which are impossible or impractical to recreate on Earth, like the behavior of the shuttle's booster rocket or the effects of traveling at 25 times the speed of sound.
The numerical aerodynamic simulation effort is already working at computing the flow field around a vehicle that will take off like an airplane, but instead of leveling off at 40,000 feet as you do in a typical transcontinental jet, you just keep going 50,000, 100,000, 500,000 feet all the way out into space. And that kind of vehicle design can only be done with the capability that we have here at Ames.
The equations governing fluid dynamics have been known since the 1840s, but the complexity of these nonlinear equations is such that some were never solved until supercomputers provided the necessary speed and number-crunching power.
There are some very interesting flows that we've never been able to calculate until the advent of high-speed computers. An interesting case is the flow near the speed of sound, which is called transonic flow. Mathematicians tried for 20 years to solve that flow field with normal mathematical techniques, and they never could get an answer. And it wasn't until the computer got big enough that people could model that on a computer that we could get answers to those questions.
The immense computational strength of NAS's Cray 2 is useless without a comprehensible human interface, which in this case depends heavily on graphics.
Let me say that the use of graphics is key because it's very, very important that the user, who is, by the way, a highly trained aerodynamicist, gets to picture the physics of the phenomenon. And again, he can use a trial and error method by using making a change which you can see, and then seeing what effect that has.
NAS's focus on user-friendliness extends to the network's uniform operating system and open architecture. Unix is the common system for all 8,000 or so users, whether the gateway is via PC or mainframe.
You can do things in a workstation like you open up a window in your workstation, and that's a window on the supercomputer, while you open up a window of some other computer. And those kinds of more sophisticated tools that one looks at in the workstation environment we're porting over into the entire supercomputer environment. We thought that was important because we saw the need for different classes of computers in a supercomputing environment to support the big number crunchers. But also we saw it was important to provide a base that we can grow from, so we could add in new hardware and software, upgrade without having to change the operating system underneath the user.
Since the first wind tunnel was constructed over 100 years ago, aerodynamic testing has changed only in its refinement. Designers can test at higher speeds using more sophisticated modeling techniques. And while the arrival of supercomputers has made it possible to simulate many aspects of reality, there is a limit to the level of detail.
The computer is very good at getting very preliminary data, and it can very quickly look at a very large design space, many designs. And then the wind tunnel is very good at getting very precise data on extremely complex configurations. And it's kind of like it can do it at the rivet head detail level, where the computer, we just don't have enough computer power to do that.
The simulation capabilities central to future aerodynamics have opened up new possibilities in other sciences as well. Researchers can now study events that are either too complex to reproduce physically or that extend beyond earthly limits. NAS can mimic the climate on other planets, examine the dynamics of exploding stars, and even colliding galaxies. Ultimately, scientists at Ames expect the NAS system to become a kind of aerodynamic advisor, much like the expert systems based on artificial intelligence.
One can conceptually conceive of doing, of actually being able to use a system that would really combine the aspects of how do I design it with how do I do the analysis to find out what kind of design is and then iterate on that. We have, in fact, done work in that area, but reasonably primitive, not to the whole, the idea of designing a whole airplane. That's a direction of research that is picking up momentum and is extremely interesting. And you can think of it as an expert aerodynamicist.
The multi-million-dollar NAS facility is the starting point for what has been called a new era in aerodynamics. And to NAS scientists, the ultimate success of the project depends on always having the ultimate in supercomputing.
Now, during the 1970s, this country maintained its leadership in simulation capability primarily because we had leadership in the availability of large-scale scientific computers. Our engineers and our scientists had access to facilities that weren't available to our commercial competitors. Now, that situation changed in the early 1980s. It began to erode with the installation of U.S. supercomputers in Europe and Japan, and also with the Japanese very aggressively and successfully developing their own powerful supercomputers. We believe that the NAS program is helping to restore and maintain a clear U.S. leadership by providing an early test site for newly developed computational technology and products.
No discussion of supercomputers would be complete without talking about superconductors, material which enables electricity to travel faster and cooler than ever before. In research labs and on campuses throughout the world, scientists are literally working around the clock to surpass breakthroughs that happen nearly every day in this exploding field. The University of California at Berkeley is home for several such scientists, including Dr. Paul Richards.
It really comes down to very technical, practical details. To build a superconducting computer, every single component that goes into it has to work well and to be practical in the sense that it can be built in large scale in large numbers. And there is a bit of a hang-up with the memory.
Memory is the major problem, and this is critical. Superconductors simply cannot hold data as well as the silicon-based semiconductors found in today's supercomputers. And before research goes much further, a new kind of memory cell based on superconductor material must be invented. Meantime, superconductors will get quicker commercial application in analog to digital converters, or simply put, input devices such as infrared radiation detectors. They will also be used in electromagnetic research that could ultimately lead to levitating trains or practical electric cars. It may be years before we see superconductors used in the transmission of energy, the building of super trains, or the shrinking of supercomputers. But it will happen, and the race is on. At UC Berkeley, for the Computer Chronicles, I'm Wendy Woods.
When J. Robert Oppenheimer first came here to Los Alamos, New Mexico in the 1940s to work on the Trinity nuclear device, all he had to work with was a mechanical calculator that worked at a speed of 1 arithmetic operation per second. Well, today's scientists at the Los Alamos National Labs have supercomputers that run at speeds of 800 million operations per second. In fact, there are probably more supercomputers here at Los Alamos than anywhere else in the world. Los Alamos was the testing ground for the very first Cray-1 supercomputer in 1976, and the lab still runs one of the earliest production units, serial number 4. Today, the lab's computer center has a total of 18 supercomputer processors distributed among 8 machines, including several Cray XMPs. Over 8,000 users have access to 40 trillion bits of storage. The multi-level security network physically separates computers working on classified computations from those running unclassified codes. The Los Alamos Computer Center claims that they perform more calculations in 24 hours than were performed by all humankind prior to 1970.
We've always been at the forefront. Our requirements have always needed machines faster than what were available, and we're still in that position. We need machines today that are 100 times faster than anything we can buy.
The Los Alamos National Laboratories were established in 1943 to work on perhaps the most secretive military project of all time, the atomic bomb, known only as Project Y. The lab's primary research role continues to be in nuclear weapons research, designing missile warheads, detonating weapons underground at the Nevada test site, and now designing SDI, or Star Wars devices. But the lab's peacetime research has expanded to include a wide spectrum of non-weapons-related projects as well, and supercomputers play a pivotal role.
What we are trying to do is simulate Mother Nature on a computer. We are trying to actually do mathematical experiments as opposed to having to set them up in a lab. We are not at the point, the machines are not fast enough yet to really allow us to do that. I think we are really approaching that area, and some areas of science are further advanced than others. But we are actually approaching the point where we can simulate nature on computers.
One of the many promising computer simulations is the Transient Reactor Analysis Code, or TRAC. The TRAC program simulates potential nuclear reactor failures, like this playback of the 3 Mile Island accident. Like NASA's simulator, TRAC relies on a graphics interface to indicate visually what is occurring. The color scale indicates the presence or absence of cooling water, where blue indicates water and red indicates steam. A modified scenario shows what would have happened if the accident had been properly handled. While the model was not designed to predict the course of a reactor failure, it can integrate sensor information and present it graphically, helping the operator to take corrective action before it's too late.
In the past, what happened was, when you got your results from a computer, on small computers, you get a page of numbers that you try to interpret. And as machines got more sophisticated, they were able to spit out more detailed data, and you started getting huge listings of printout. And it's very difficult to interpret that. Human beings are just not equipped to interpret that. What human beings are equipped to interpret are visual images.
Recreating reality, or potentially real events, can be as frightening as it is exciting to watch. This model simulates a nuclear winter, the predicted climatic change that would occur after a nuclear holocaust. Smoke particles in the atmosphere would block out sunlight from a large portion of the Earth while permitting radiational heat to escape. The result would be abnormal cooling of the Earth's atmosphere. Blue particles represent the movement of smoke in the lower atmosphere up to 10 kilometers above the Earth's surface. Yellow indicates how the smoke would disperse at altitudes above 10 kilometers. Paradoxically, the lab's supercomputer facility plays a primary role in modeling the nuclear detonations that would create a nuclear winter.
There are a lot of experiments that you can do in a laboratory that you can't watch happen. For example, a nuclear explosion in Nevada. You can't stand there and watch that happen. Whereas if you can simulate that on a computer, you can actually watch the interaction of the materials. You can see what's going on. And if you've done your mathematics and your physics well, what you're looking at is exactly what happens.
The clarity of a pictorial simulation on a color screen can be deceptive. While the image is attractive, the underlying equations and algorithms are responsible for its accuracy.
If you don't have good science, supercomputer is not going to help you, and you must maintain the elegant science. What we do is try to find codes, computer programs that are using a lot of time, and go to the owner and try to help them make the codes more efficient. And in doing that, we look at the algorithms and what's going on.
Some of the most beautiful simulations at Los Alamos are part of a project that is exploring the interaction of a high-speed gas jet when injected into a gas of a different density, as much as 100,000 times more dense, at speeds of Mach 10 or higher. This phenomenon, which has been observed in outer space, is part of a research project into the fundamental physics of nature.
We know a lot more equations than we can solve. And what you were forced to in the past, and we are still forced to it, to make more and more simplifying assumptions till we finally end up with a tractable set of equations. Now, if compute power goes up tremendously, and with parallel processing and faster chips and new technologies, you expect that to go up even further. What that then allows you is to go towards the more fundamental equations without the simplifying assumption, so that for the first time you really have a chance to compute the basic laws of nature as we know them.
The flexibility of a simulated model permits the scientists to change rapidly the variables of velocity, density, and pressure of an experiment that no wind tunnel on Earth could recreate, and the computing requirements are massive.
The computations we did just in the first 2 months of this year required as much computer time as I probably were able to use in the previous portion of my life. So basically what it allows you to really let your imagination roam and really begin to address fundamental physics issues, so that you don't try to hop like a butterfly from one flower to another one and just skim off a little bit. But I think with the resources which are available at the lab, if we couple them with a sort of environment which we really need now, one really can dig deep in a particular area.
Karl-Heinz Winkler hopes for a time when his experiments will not be restrained by hardware or software limitations, but by his own imagination. And he believes that will require a radical change in computer architecture.
Well, in terms of performance for an individual CPU, I think the supercomputers we have here already have a phenomenal track record. So if you get there an additional performance of a factor of 2 or 3, that would be just outstanding. So in order to get the orders of magnitude higher performance we really need, you are necessarily forced to parallel processing machines. That means you need hundreds of processors to do the job in parallel. And so I would expect systems to come up in the next 3 to 5 years, which are several hundred times in throughput one of these, now over 10 years old processors.
As impressive as the supercomputers here are, they are nothing compared to what's coming. The new Cray 3 supercomputer is being designed now. It'll be available in 1990, and it'll operate at speeds 500 times faster than a Cray 1, and it will be small enough to fit on your desktop. Indeed, one computer scientist here says that by 1990, you'll be able to get the speed of a Cray 1 in a desktop PC. That's our look at supercomputers. We'll be back in just a minute with this week's Computer News.
I'm Susan Chase, sitting in for Stewart Cheifet. In the Random Access File this week, supercomputing news continues to make headlines. At the Los Alamos National Laboratory, work is being done to develop a mathematical computer model to determine the spread of the AIDS epidemic in the United States. This model will predict the spreading of the infection and the development of AIDS in various population groups. And looking for super speed without the super cost, Sky Computers of Lowell, Massachusetts produces a product called the Vortex AT board, which can be installed installed in your personal computer. The board allows an AT to work near supercomputer levels for a fraction of the cost. In the $10,000 range, the board is not meant for the occasional user, but it is a small price for companies who want to own their own supercomputer. In other news, there are reports of hardware problems with the IBM PS2 models 50 and 60. Software developers report phantom mouse and keyboard errors, which have eventually led to failure of the motherboard. In addition, there are reports of intermittent hard disk errors when running DOS 3.3. IBM, however, is standing by their machines. Service centers are replacing the system board in defective machines, and the company has contracted Microsoft to correct the problems in DOS. It's time for this week's software review. Here's Paul Schindler.
When you wish upon a star.
Jiminy Cricket's song from Walt Disney's Pinocchio. In this case, the star, though, is the Cricket Graph. It's probably the best business graphics package now available for the Apple Macintosh. Like most graphics packages, you can import data from elsewhere or start by filling in a table. This chart is a sample of what you can produce with the package. You have a choice of 12 different kinds of graphs. Among them are scatter, line and area, bar and column stacked or side by side, and pie charts. And for the scientist, there are polar and QC charts. Cricket Graph shows more flexibility than most packages. It allows you to easily select which information you want to plot on each axis. It redraws its graphics quickly, and it offers lots of variations within each graph type. Now, you decide whether you want your output to the screen, to a printer, to a word processor, or a desktop publishing program. Cricket Graph for the Apple Macintosh is $200 from Cricket Software in Philadelphia. For the Computer Chronicles, I'm Paul Schindler.
A new conference for computer professionals has been announced. The World Congress on Computing will make its debut in Chicago in March of 1988. The conference, organized by the Interface Group of Comdex fame, intends to bring together manufacturers with the professionals responsible for the acquisition and implementation of business systems. Asher Technologies of Roswell, Georgia has come out with a facsimile product for IBM-compatible portables. The JT Fax connects to the computer via the serial port. It measures 1/2 inch by 6 inches and sells for under $500. First, there was computer-aided design. Now there's computer-aided writing. A company called TextGen of San Mateo, California, has developed a program by the same name that writes letters for you. TextGen creates a letter from your answers to a series of multiple-choice questions. If you don't like the letter, TextGen will try again or allow you to edit its letter manually. Finally, do you know what country leads the world in the number of computers per person? Or who has more employees overseas, the State Department or IBM? Answers to these questions and more can be found in Future Computing's Computer Industry Almanac. The Dallas-based company calls the book an insider's guide to the people, companies, products, and trends in the computer industry, but also serves as entertainment for trivia lovers. And to answer the earlier questions, the U.S. leads the world in the number of computers per person, with 146 in use for every 1,000 people. And IBM has over 160,000 employees overseas, compared to the State Department's 16,000. And that's it for this week's Computer Chronicles.
The Computer Chronicles is made possible by Leading Edge, makers of IBM-compatible computer systems, including Lotus Lookalike Spreadsheet, word processing with spelling correction, communication software, and Hayes-compatible 1200 baud modem. Leading Edge, with over 1,000 service centers nationwide. Additional funding is provided by McGraw-Hill, publishers of Byte. Byte's detailed technical articles on new hardware, software, and languages cover developments in computer technology worldwide.